Yeah, so everybody, I'm Derek. As Aaron introduced, really, I really appreciate those kind words. And I think before jumping into all the weeds here of my thesis, I really wanted to like honor and acknowledge the opportunity to be the last presenter for this quarter's thesis. Students, the work that everybody's been doing has been awesome, and it's been honest joy to get to stick with everybody along the way and hear about all their hard work. So, it's going to be hard to follow all of that here, but I'm going to do my best. So anyway, kind of jumping into what I'm working on. I was really interested in understanding soil organic carbon dynamics in forests here in Washington. And in particular, I was interested in building a predictive model. I thought machine learning, and we found that machine learning provided a relatively novel approach and an opportunity for small forest owners to really jump into the carbon modeling field. So to give kind of there it goes. To give kind of a brief overview of what we're talking about here, we understand that soils are the highest and the largest terrestrial carbon sink worldwide. The carbon that's stored in the soils is stored in two different forms. There's organic carbon, which is primarily made up of organic material inputs into the soil, and there's inorganic carbon, which is usually produced through weathering or other mineral deposits. Corey gave us a great rundown, really in-depth rundown of those things in the last presentation, so I won't bore you with more details there. In the context of my study, we found that soil organic carbon in Washington forests in particular is of a lot of interest right now. This is not only because it's really variable in these forests, but it's also really vulnerable due to the timber harvest industry going on here. We know that timber harvest leads to a really immense short-term loss of soil organic carbon, followed by a period of recovery, but still resulting in an overall loss. In the context of climate change, this carbon loss is released into the atmosphere through carbon dioxide, and it's of our interest to try to reduce the amount being released. This is compounded by the fact that a vast number of the forests in Washington that are used for timberland are owned by private owners that are small forests under 20 acres. This map here in the bottom right is really indicates all of the forests that are owned that are under 20 acres across Washington. And the cost of understanding where carbon is stored in a forest would be so prohibitively costly to these small landowners that they are unable to make educated management decisions with regards to where to cut down the trees to not release the carbon, that sort of thing. So as a goal for my project, on top of the quantitative research, it would be to build a framework and a workflow for people who own small forests to be able to develop a map of soil organic carbon to more easily understand it and measure it. I believe machine learning provides a good opportunity, as I described before, because it's known for being able to take relatively small data sets and produce ecologically representative results and in really complex systems. So this led to my research question, which is how effectively can a random forest algorithm machine learning model predict soil organic carbon using field or easily measurable variables at single watershed basin scale? So I'll first kind of talk about my study site. I had the wonderful opportunity to research at Ellsworth Creek Preserve down in the southwest of Washington near Willapa Bay. This preserve is a 7,300 acre preserve owned by the Nature Conservancy. It's really, the climate there is really characteristic of our coastal temperate climate, where the winters are wet, the summers are cold, and it's barraged by heavy wind events. It's owned and operated by the Nature Conservancy, who prior to their purchase in the early 2000s, it had been managed for timber harvest really actively for about a century. The Nature Conservancy has basically opened this space for scientific research for their partners like Evergreen to go and conduct research like mine. In this preserve, they delineated 8 watershed basins, and for this experimental analysis, I selected the northernmost subbasin. This subbasin is a control basin with regards to their study design. That basically just tells us it's been unmanaged for the last 20 years, by and large. In this subbasin, they established 26 vegetation plots, separated each of those into 4 subplots about 9 meters from the center of each plot, that in the cardinal directions, north, south, east, and west. So 14 of these big macroscopic plots were sampled as part of my study, and 3 of them were sampled by previous work going on here at Evergreen by Dylan Fisher and Stephen Quick. who really generously shared their data and their study design with me and allowed me to build it out. So overall, I collected 54 total samples to a 10 centimeter depth, including the O horizon across the subbasin, and 12 sample data set was provided by Dylan Fisher and Stephen Quick. For my samples, I extracted the O horizon in the lab and analyzed them for percent carbon and percent nitrogen using elemental analysis here on campus. Well, not here, the Royal here. So using this data that we gathered for soil organic carbon, the next step when building a predictive model is to understand what variables to predict these measurements. So to kind of look at that in the big picture, let's take a look at how carbon is cycled briefly in soils across the world, and particularly in forests. So it's really driven by three primary indicators. The first of which being organic material inputs through above ground litter fall or below ground root growth. That organic material is then contributed into the soil, where it begins to decompose and be respirated by the various organisms that live there. When it's decomposed and respirated, it's released as CO2, and that process is primarily controlled by temperature and moisture. So on a really macroscopic perspective, we can really consider three big picture controllers of soil organic carbon in these soils, which is organic material inputs, temperature, and moisture. So when we selected our variables to measure in the field, we considered analogs for that, for those three characteristics. We selected 6 variables separated into an ecological category and the topographical category. The ecological data was provided by the Nature Conservancy. They gathered that data in 2020, and that consists of overstory cover, which we anticipate would have a positive relationship with soil organic carbon. When there's more canopy cover in the woods, we would expect more carbon storage underground. That's likely due to more inputs from the trees themselves, and also we understand that under the canopy in a forest there's microclimate systems where temperature and moisture is affected. Understory cover, it was another data set that we were provided, and that really measures the understory growth in the forest, and similar to overstory cover, we would expect a positive relationship. And I think the last and most complex and interesting relationship and data set we received was stand age. Not only do we know that older trees are larger and they provide more input, like the plot seen on the right here, but we also, in a second growth forest like Ellsworth Creek Preserve and our subbasin, it's also an analog for the time since last timber harvest. So it's really also looking at the effect of timber, and which we know is complex but important in the conversation of forest carbon. On the topographical side of things, we used a public USGS database using LiDAR to evaluate elevation, slope, and aspect. For elevation, we would expect higher carbon storage at higher elevations because it's colder and the soil is drier. For slopes, we would expect an inverse relationship. Steeper slopes not only have greater erosion and duff runoff for the organic layer, but they also, water flows downhill and there's more sun exposure. And then, of course, aspect is really important when we're at these high and low latitudes like here, because the south-facing slopes are going to have significantly more sun exposure, kind of as Renee described for her solar presentation. So with all this data, we combined it into a rainforest model, and using spatial data sets, we were able to produce a predicted carbon raster using GIS. And then we're able to perform hotspot analysis. So this workflow really presents the opportunity to go collect a little bit of field data, measure some data in that field, and then be able to produce a predicted carbon value across your entire forest. So I keep mentioning machine learning and model generation. So briefly, I'll talk a little bit about what that involved. So rain and forest analysis, the algorithm that we utilize to generate our model, uses classical kind of decision tree analysis. A lot of us have probably seen decision trees in our day-to-day where to describe project management and that sort of thing. And this is a machine learning method that utilizes these decision trees to make predicted results. You have nodes that form into 2 branches. In our case, in the big picture, one direction is when a variable is above a certain value. The other direction is when a variable is below a certain value, and that continues on to form a decision tree. When we collect a bunch of decision trees together, we call that a forest, and that's where rainforest got its name. So in the context of our model, we built a 1,500 decision tree forest using random subsets of the data across each of those 1,500 decision trees that forms our random forest. Each node also uses a random variable to select the split, which kind of creates this big multivariate relationship and why it's good at predicting complex systems. I think the big takeaway with random forest analysis is that it's very hard to interpret. You know, I can't sit here and show you my 1,500 decision trees. And it's really hard. I don't have a nice equation to show you at the very end. And that's why we perform the raster analysis to develop the heat map and the hotspots. So to perform that, we generated 6 spatial rasters of our data sets. You know, LiDAR is relatively continuous. We were able to just use the LiDAR data. For overstory and understory cover, we used interpolation. And then for stand age, the Nature Conservancy provided historical timber stands for us to generate our spatial data sets. So using all those methods, we came together and we found a few pretty interesting things. So first, let's talk about what I found in the field with my field measurements of soil organic carbon. So across all of the sites, I found a median carbon value of 284 megagrams of carbon per hectare. Those who have done some research on soil organic carbon, especially in agricultural settings, this number seems extremely high, and this is why the forests are really notable here in Washington, because they're known for storing immense amounts of carbon. This value is actually not too far out of bounds from what we would from what other studies have found. A meta-analysis in 2014 found 211 megagrams of carbon per hectare as a median value, which is relatively close to what we found. Unfortunately, due to the sample size and the just general complexity of these relationships, the classical statistics, the non-parametric correlation statistics we performed were largely unsuccessful. There were very few significant relationships we found with our variables. And as I said, this is probably due to sample size and the complexity and the nonlinearity of the way each of these variables behave. Taking this carbon data and bringing it together into our model, we evaluated this model using the R-squared, the coefficient of determination, and the root mean squared error, or we can just think of it as the error. So our R-squared value was 0.87. That's pretty good in the context of ecological studies. That's actually very high. This indicates that our model does a really good job of taking the input data we provided it and building a model using that. It's able to account for a lot of the variance in the data we provided it. Our error is sort of conflicting with that idea because our error here is moderate to high, especially in the context of a lot of modeling, though it's not out of bounds from what other research has found. Our error was about 165 megagrams carbon per hectare. You can see on the plot here on the bottom right, this is the predicted values across the subbasin, and the width of 165 megagrams of carbon really shows you how much error there is for each of these predictions, and how that's sort of conflating with the fact that our high R-squared value. The interpretation of all this means that our model is likely overfitted. That means that our model took the data points we provided it and drew by and large a straight line to connect them all. So it's not very good at taking new data and building ecologically representative predictions as well as we had hoped. We also evaluated how the model was performed with regards to each of the variables we provided it, and including a 7th variable to test for pseudo-replication. The overall takeaway from this top plot is that all of the variables provided relatively consistent and even contributions to the model. This is good news, which means the 6 variables we selected were all necessary to make our carbon predictions. It's also some challenging news because it means that the pseudo-replication tester variable provided some strong contribution too. This likely means that there's some pseudo-replication going on in the study design and is an opportunity for future growth. So in the context of individual variable relationships, we characterize a forest here in the subbasin that's really dense with a thick overstory and relatively sparse understory because of that thick overstory. It's relatively old with a median age of 75 years, though there were still timber stands that were only 4 years old when the data was collected in the early 2000s. Excuse me. I think the most interesting result here is in the bottom right. We have Our model was able to predict a relationship with soil organic carbon, where it showed a relatively steady decrease following timber harvest, and followed by a period of recovery at about 50 or 60 years. This result is actually very similar to a historical and colloquial finding that's pretty well referred to in timber research, known as the Covington curve, visualized next to it there. While it's not a perfect match, I think this provides some credibility to our model at predicting ecological relationships, even if what we're finding doesn't necessarily reflect what previous research has found. On the topographical side of things, this subbasin was extremely topographically variable, ranging from basically sea level to 600 meters with steep slopes. The aspect was largely dominated on the eastern and western sides here on either side of the river. The most interesting findings here have to do with slope and aspect. For slope, we found that carbon really sharply dropped off at over 35 degrees. This is likely due to the duff erosion that we described, where the high wind and weather events that we encounter likely pushed this top organic layer down slope and causing the total carbon stored in that region to be lower. Additionally, for aspect, we actually found the opposite of what previous studies have found in the context of carbon storage, where the southern-facing slopes were storing more. This could and is very likely due to sample size implications, but there are also potential implications from weather events. The north side of the subbasin feeds into the Nasile River and Willapa Bay to the north, which is where the weather events would be coming into the subbasin, which means that the south-facing slopes are going to be protected, and the runoff caused and erosion caused by those weather events is going to be lower on the south-facing slopes. Using all this, we brought it together into a heat map here on the bottom left and perform hotspot analysis here on the bottom right. These are really strong approximations. Not only is it a model that we already described the limitations of, but it's also using approximated interpolation and that sort of thing. So think of them as a proof of concept and a way to visualize some macroscopic ecological relationships. For example, here we see that the southwestern region of the subbasin is storing higher amounts of carbon, and this is likely due to the fact that it's higher elevation, it's lower slope, it's an older forest stand, and they're also predominantly southern-facing slopes, as we described before. We also see in the lowland regions where there's periodically standing water and less overstory cover, we're actually finding less carbon. This is likely due to the temperature effects, and then also potential effects from like runoff from the water dynamics and the drainage features here in the subbasin. So to kind of bring it all together here at the very end, as part of my study, we built this predictive model using field measurable variables and lab analysis of soil organic carbon. I think the model itself, the model I described here, has some serious limitations. There's indications of overfitting and pseudo-replication, in addition to just a moderate to high error in and of itself. This is likely due to the sample design, as well as some fundamental flaws in the field and sample design, in the field and sample design, as well as sample size. But I think the cool story we've captured is the capability of machine learning, in particular random forest analysis, to fight through these limitations and produce ecologically representative results, such as the stand age and Covington curve relationship. And I think we've achieved our goal of building the foundation to lower the barrier to understanding where carbon is being stored. Even if there's some relatively wide error bars, you could still make decisions based off of these maps we produced today. So at the end of my presentation, I really want to acknowledge, Aaron and all of the experts who provided a lot of insight for my study. Dylan Fisher and Stephen Quick, basically walked me through their whole study design process. And Michael Case from the Nature Conservancy gave me access to this really beautiful preserve. When I was out there, I had to be with somebody in the field for safety reasons. So all of these individuals who came out and dug holes with me in these steep and variable slopes, I couldn't thank you more, and all of the help along the way. And I'm happy to take any questions.